Right, salam again. Let's have a look at modulus argument form now. So basically a modulus argument form is a way to express the same complex numbers that we were analyzing previously. And we've got a new form to introduce. Now, you guys are already familiar with Cartesian. Cartesian is pretty much what we've been doing in these last two sections here and these last two examples. But basically Cartesian form means if I'm given if z equals x plus iy, then I'm just representing it in terms of x and y. So maybe we've got a point here. This point here will have coordinates x and y, and that's purely based on the numbers x, y, and that's done. So what that means is we've got these numbers here. If I can get this straight, this here lines up with the value x on the real axis, and then this here lines up with the value y on the horizontal axis. Sorry, not there, up here. And that would represent y. So straightforward. Cartesian you're familiar with. I'll just write a little subheading. This is Cartesian. Okay, polar is a bit different. Polar expresses the complex number in terms of a modulus. So what's a modulus, you might ask? I'll explain that down here. But basically it represents it with a length from the origin, and then we have this special trigonometric identity. Okay, we're obviously going to delve into this part a little bit deeper, but polar coordinates will have, oh, I shouldn't be putting numbers yet. Z equals to r cos theta plus r I sine theta. Yeah, so just ignore the form at the moment. What I want you to understand is the length here is represented by r. We know we can also express it as mod z, so I might just do that. But let me get this first. Put this point here. We actually do not need that. Okay, so basically what it is, this here will be r, the length. Now I'm going to change to mod z. I just feel like it's a bit more concrete. All right, so we're gonna express it as mod z for the timing. I'll change it to r in the middle of the question. But basically mod z is just a number. Okay, I think I mentioned that earlier, didn't I? Oh no, not yet. We'll look at mod z soon. Mod z basically represents the length of this line. See this line? It's talking about the length of this line from the origin. So mod z, or we could even call it r, and the angle theta. If you notice, this form contains the modulus and the angle. Hence why we can represent it in what's called polar form. So polar form means expressing a unit in terms of its length and its angle. Kind of like bearings if you think about it. When I ask for when we talk about positions with bearings, we generally talk about how far away it is and in which direction. This is the same thing. How far away it is from the origin and in which direction. And direction can be determined by an angle. Okay, so that's the introduction to the difference between Cartesian form and polar form. So now let's dive into polar form and figure out what this word that I've been saying is, modulus. So at the bottom here, we've got the definition of the modulus. So the modulus of the complex number z is mod z. So this is what I call mod z. I'm pretty sure everyone does. I call this mod z, which is the distance. So look at that, which is the distance of the complex number from the origin. That is the most important aspect of this. If I put a complex number here, its modulus is this length. If I put a complex number here, its modulus is this length. Always back to the origin. Okay, all modulus are measured from the origin. Okay, so the modulus of complex number z is mod z, which is the distance of the complex number from the origin on an argand diagram. Okay, and if we observe this carefully, we can identify this by using Pythagoras theorem. Like if you look at the Cartesian form, you will know the length here or the length here, and if I need to put into polar form, I just have to find I just have to use Pythagoras theorem, as you can see down here. See, if z equals x plus iy, well, if we look at this diagram, this is x, this is y. It's just x squared plus y squared equals that squared, and then you square root it as indicated here, and you've got your modulus length. And that's all there is to it. Modulus is one of the easiest things you can calculate. Okay, and now the argument. The argument, this is a funny word to call something. I'll make it brief. The argument is actually the angle. And since you guys know 2-unit quite well, all you have to do is use trigonometry to find this angle. And if you look, you got a right angle triangle. The two most obvious sides you'll be given are this and this. If you have that, you can see that's opposite over adjacent, and we generally use tan to find the angle created by the complex number. Very straightforward. So if we look here, the argument of the complex number z in arg z, which is the angle that the interval makes with the real axis, is in the positive direction. So that's the angle, or it's always measured from this side to that way. So if a complex number is over here, I'm still measuring from this side to this side. And it even holds true for if the complex number is down here. We measure from the real axis positive side to that complex number. And it even works if it's down here. Measure from the real axis to the complex number. It's always coming off this line first. So the right side of the real axis, the positive side of the real axis, we measure our angles from, or our arguments from. Now, a few important notes. The argument of a complex number, z, is written as arg z, which is the angle that the interval makes with the real axis in the positive direction. So we just mentioned that. And there's an important note on which angles we measure our complex numbers from. And the argument of complex number is usually measured between negative pi and pi. Okay? What I mean by that is, from, let's say this is 0, and I'll extend this line just a tad, then it means if I'm above here, it's pi, and if I'm below here, my extreme, actually let me explain that again. My limit for the positive part of the real axis is negative pi, so I'm going to end up at negative pi here. Oh, I said that incorrectly again. Scratch that. It's positive pi. Okay, so positive pi, from 0 to positive pi, that's the angle there. And in the negative direction, so let's say complex numbers are below the real axis, then my angle will measure up to negative pi. So we actually get a reset here. Okay, we do not exceed these, and there's a very good reason for it. If you recall conjugates, doing it this way will make manipulating complex numbers far easier. If we use 0 all the way around to 2 pi like we normally do in 2-unit trig, like that's 0 to 2 pi, we can get a bit confused. It is much safer to do 0 to pi for the positive real axis and 0 to negative pi for the negative side of the real, what is it? The above the real axis and below the real axis. Okay, so that will be the way we operate. So now let's have a look. We're going to observe these forms first. So real quickly, if I have an angle in this quadrant, and we understand our quadrants, if we're in this quadrant, then let's say this complex number is z, then its theta, or its angle, is between 0 and pi on 2. So 0 less than theta less than pi on 2. So basically, if I know the Cartesian form of my complex number, and I know it's in this quadrant, then it's pretty straightforward. All I have to do is calculate the acute angle for this result. Okay, and that will be, if we look at it, if that's xy, then it's y on x. So that's really a tan. Tan theta equals y on x. Okay, so you will need to remember that. Theta in this case will equal to tan inverse y on x. So that's the rule for the first quadrant. Now, for the second quadrant, which is over here, let's say our complex number is here. Okay, so our complex number is there, measured from the origin. I have to stick to the rules from earlier. I'm still measuring off the positive side of the real axis. So that means I have to measure this way. That there is theta. And let's say this is my complex number z. Well, this angle we can tell is between pi on 2 and pi. So now when I want to calculate the actual angle, I have to calculate the acute angle first. And then once I've calculated the acute angle, if you look at the acute angle, it's still going to be the same rules. You do rise over run, okay? And just keep everything positive. But when we calculate it, theta will equal to pi minus tan inverse y on x. Now I'm going to use absolute values because I'm just saying these values need to be positive in order for it to work out this way. I'm not asking you to memorize this, but be aware that we're looking for an obtuse angle in this case. So whatever you can do to help you memorize it, just tell it to yourself. Maybe we can do descriptions. I think a description might help. This is going to be acute, so that's quite easy. Actually, I'll do it in orange. This is going to be acute. So that's easy, you just tan inverse it, it'll work. But the angle over here is obtuse. So you have to make sure that you're subtracting it from 180, or in the case of radians, subtract it from pi. All right, let's move on to the third quadrant. Actually, this is the third quadrant. So the third quadrant, we have, let's say we have an angle here. And just real quick to backtrack. Here, in the first quadrant, x will be a positive value, y will be a positive value. Because look, positive x, positive y. In the second quadrant, x will actually be negative. See, these are all negative x values. And y will be positive. Just a few more things to take note of. In this, the third quadrant, x is negative and y is negative. So there's many identifiers for how you should set up your angles. A lot of things here I can tell you how it's going to work. Now, the third quadrant rule follows what we said about negatives. So in terms of negatives, I will measure my angle from below the x-axis, or below the real axis. And this angle here is obtuse, but there's a catch. So we can see it's similar to this, it's obtuse. But the angle here is between 0 and negative pi. So I think we write the negative number first. Negative pi to 0. Because we're going negative pi to 0. Okay? So that's the obtuse angle. So there's a catch here. It is obtuse, but it is also negative. So it's a negative obtuse angle. And you need to be aware of that when you're calculating this. And the calculations we use are similar to this, except we use theta equals negative. So we've got to negate the entire result and then just do pi minus tan inverse the absolute value of y on x. So that just means make the triangle's values positive. Because we're going to have negative x values, and negative y values. So just make them both positive, hence why I put an absolute value like this. And you just work out an obtuse angle, and we all know how to do that. We do pi minus tan inverse of whatever you're trying to calculate, and then just put a negative in front, and now you've got a negative obtuse angle. And finally, we have, that's Z, by the way. Finally, we have when we're in the fourth quadrant. As you can see here, x is positive, y is negative. And this angle is acute, but it's between negative pi and 2 and 0. So notice this theta is below the real axis, and it's negative, but it's acute. So it kind of makes it a bit easy. If I want to know the theta of this angle, I will just do negative tan inverse, so just maintaining that it's negative. Just solve it like a normal triangle that has positive values. Okay, you don't have to put the absolute value in your calculation. You can just make them positive. Like if that's 3 that way and then negative 4 this way, just make this 4 when you're putting in your calculation. That's all I mean by that when I say that. But because it's acute, it's just rise over run, the tan inverse of rise over run, and putting a negative out the front. Okay, I know that was a lot to digest, but it's actually good that it's in video form now, because you can go back and look at this until you fully grasp it. But let's move on and see how we can start bringing this all together. Now, we learned this Mod-Arg form because of the expression that I showed you here earlier. This is a way that we actually represent our complex numbers. It looks very complicated, but it's actually quite easy to understand. But let's explore this properly. So now the complex number z equals x plus iy can be expressed in modulus argument form. So here's our complex number. We know it's z equals x plus iy. So if I set up my triangle, I have x as the horizontal coordinate, y as the vertical coordinate. We have mod z. We're just going to assume mod z for the time being is the length from the origin to the complex number. And then we have theta, which is the angle created. So from the diagram, if I just do some basic trigonometry, so let's look at the cos of this triangle, of cos theta of this triangle, and we can see that we get x over mod z. Okay, so making x the subject, I will end up with x equals mod z cos theta, if my pen computes that. All right, secondly, let's take the sine of this triangle as well. So sine theta is now opposite over hypotenuse, so y over z. And we end up with y equals mod z sine theta. So we've got these two identities. Now, real quick, if z equals x plus iy, as we've got here, then watch what happens when I replace x and y with my new identities. Then z equals mod z cos theta plus I. We've got an I there, but I'm going to write the mod z first. Actually, no, let's just follow the order. I mod z sine theta. So just a quick recap. Can you see how I've subbed y, x and y with their respective counterparts above in the identities I just derived? Well, this is your complex number representation. Pretty easy, huh? Okay, with this, we can see that mod z is equal to the identity we observed earlier. So mod z, and I'm also going to let it equal to r, because it's just an easy way to express it, is going to be the square root of x squared plus y squared. just use Pythagoras theorem. You can see x squared plus y squared equals mod z squared. Square root it, you get mod z equals to square root of x squared plus y squared. And also the argument, get used to the language, the argument which we're going to call theta is just, in this case it's acute because it's in the first quadrant, so I'm just going to assume it's acute. We're going to say that this is equal to tan inverse, and you can see rise over run, y over x, or opposite adjacent. All right, this is essentially how we find all our complex numbers. So to bring that all together, z equals r cos theta plus I sine theta when I factor out the r. And guess what? We have an abbreviation for this. We call it r cis theta. And this is the polar or the mod argument form of a complex number, and we use this to simplify the way we write some of these results. All right, hopefully that wasn't too difficult. This here is an abbreviation, so I'll just write that as a note. Note cis theta is an abbreviation of cos theta plus I sine theta. And I'm sure logically you can see how. Alright, so that's your introduction to the Mod-Arg form. Let's have a look at a few examples. Write the following in modulus argument form and sketch on an Argand diagram. So, the first thing we need to do, we want to find the length from the origin. So that's called a modulus. The modulus is mod z. We're going to use modulus. And all we're doing is the square root of the real number plus the square of the imaginary number. Work that out, you're going to get 2. And now, real quickly, briefly in your head, you can see this is the coordinate 1, 3. That means we're in the first quadrant. Hence why I've got the shape drawn like this. This is the first quadrant. So that tells me it's just an acute angle that I don't need to modify. So the argument, let me write it a bit more correctly. The argument is tan inverse of root 3. Oh, I didn't write root 3, sorry. The tan inverse of rise over run. Remember, rise is always going to be the imaginary value. Rise over run. And if you're good with your radians, you know that this is an exact value of pi on 3. Alright, with this, I know my complex number now. So therefore, z equals 2 cos pi on 3 plus 2I sine pi on 3. Because we have the modulus, which is 2. And if you look, we're going to put 2 right there in the formula. And we have the argument pi on 3, which we're going to put in the theta. And I've done exactly that. And if I was to abbreviate this, this would be written as 2 cis pi on 3. Just like that. Alright, now the easy part. As accurately as you can, draw a line that is 2 units long. Ignore the decimals for the time being. Ignore the extra notches on this graph, but we'll say that's a length of 2. This is a length of 2. And then the angle subtended is pi on 3. That's it. Okay? And to line it up with the Cartesian form, well, we can say that this here is the horizontal or the real value, which is 1. and this is the imaginary value, which is square root 3, taken straight out of the actual coordinates. So it all lines up perfectly. And the complex number would be right here. This actual dot is the complex number. This is Z. Alright, hopefully that wasn't too complicated. Let's try another example. So mod Z equals to the square root. Let me just clean that up. Equals to the square root of this number squared, so the real part squared plus the imaginary part squared. And we're not taking I, we take the -1. So that's -4 squared plus -1 squared. And this will equal to the square root of 17. And the tan inverse of this, so we've got to take a few things into consideration. Firstly, this argument is in the third quadrant. The third quadrant is a negative angle. That's the first thing I do. But it is also negatively obtuse. Okay, it's negatively obtuse, meaning I have to subtract the answer from pi. So pi minus. And then finally, pi minus tan inverse. Yep. Pi minus, sorry, I almost had to sneeze. Pi minus tan inverse of the rise. So remember, it's always the imaginary part over the real part. The rise over the run. And I'm just going to ignore the negatives because understanding that this is a negative obtuse angle, I can do it straight away like this. All right. And then we get this result. And because it's not an exact value, we will take the radian form of it as a number. So it's with 3 decimal places. This will calculate to become -2.897 radians. And that's our modulus and our angle, or our argument. So this complex number, it's written quite funny. In an abbreviated form, it would be root 17 cis -2.897. But this tells you everything. It's got a length of root 17 and then angle of -2.897. Okay, well that's actually quite flat, like it's quite close to the real axis. Let me do a dotted line here. So that means this angle here is -2.897, or as an angle is 2.897, but because it's below the real axis, we know it's negative. So that there's square root 17, and that's it. The complex number itself . So that would be, let me remove this. Okay, this here is -4, this here is -1 because of the coordinates. See, that's coordinate -4, -1. And that's that. All right. And then this graph here, z equals -I. Looks kind of complicated, but it's actually quite easy. Let's start off with the modulus. The modulus is just the square root of the real part, which is 0 squared, plus the square of the imaginary part inside of a square root. This calculates nicely to become 1. Okay? Now, here's an interesting part. So -I we know is down here. We know it's below the real axis, and it's on this horizontal line. Now, watch what happens. This coordinate is essentially 0, -1. Now, if I tan inverse this, no matter which sort of orientation we're doing it in, we have it in the negative range. So we got to put negative, and we're going to do tan inverse of rise over run. So rise is 1 over 0, But we all know that this is non-existent. We can't do tan inverse of 1 on 0. And this is a feature of the tan graph. But if you recall, there are a lot of asymptotes. And these asymptotes line up at 90 degrees. So therefore, since this value is non-existent, then that means we are approaching to 90 degrees. Or in this case, negative 90 because it's below the real axis. Okay? And because it's undefined, we always jump straight to 90 degrees when it's the case of tan inversing an undefined number. So let's go ahead, plot that in. So we have, let's rewrite it. So Z equals, so therefore Z equals, this is an interesting one, 1 cis negative pi on 2. All right, obviously we don't need the 1, but look at that. Polar form tells you a lot of information of how your graph is going to look, and that's that. It has a length of 1, it has an angle of negative 90. It's very concise and neat. It's a very interesting topic. Just everything works. But there you go. That's how you convert something into a complex number in polar form. And finally, we're going to convert polar forms into Cartesian forms. So polar forms into Cartesian forms. It's as simple as honestly just putting these in the calculator. Okay, putting them in the calculator will be good enough, but in some cases, obviously in exam style questions, you have to know there are certain exact values which you have to know. So in this case, 3 times cos pi and 4. Cos pi and 4 is 1 over root 2 plus 3i times sine pi and 4, which is 1 over root 2 as well. And look at that. Cleaning this up, we get 3 over root 2 plus 3i over root 2. And if you look, here's my real part, here's my imaginary part. If you were to reverse everything, do exactly what we did here, you would go back to exactly that if you do it correctly. Alright, so yeah, as you can see, this is quite easy. Now, here, 4 cos pi on 6, I'm going to expand the brackets here, plus 4i sine pi on 6. Actually, no, negative sine will actually be a negative. So it's going to be 4 cos pi on 6 minus 4i sine pi on 6. So cos actually absorbs negatives, hence why I didn't write a negative here. So you got to do a quick recap on your trigonometric identities. It's easy. Cos absorbs negatives, sine doesn't. That's one way to really think about it. All right, and then from here, we do 4 times, what's cos pi on 6? That's an exact value. That's going to be root 3 on 2. Minus 4i times sine pi on 6, which is a half. So I'm going to end up with 2 root 3 minus 2i. And that's my Cartesian form for that. And then finally, 6 cos 2 pi on 3, that's another exact form. Cos 2 pi on 3 is actually a negative number because that's in the second quadrant, and cos in the second quadrant is negative. That will be a half, negative a half. And then sine 2 pi on 3, that's in the second quadrant. Sine is positive in the second quadrant, so that's positive root 3 on 2. So a lot of trigonometric identities are assumed here. And simplifying these answers, we get negative 3 plus 3i root 3. And that's that. So once you've gone through this video, guys, you should be able to resume the next exercise. So if you have any questions, just post them on the group and I'll help you whenever I can. Have a good day, guys.